Right. So in the last class we were discussing on AC in R, L, C individually. Correct. So you remember alternating current when we were passing through resistor, the EMF was in phase with the current. Correct. At the same time, when we were passing the alternating current through an inductor, the current lag EMF by 90 degrees. When we were passing the same AC in capacitor, the current led EMF by 90 degrees. Correct. So this is how we were discussing on that. Correct. Okay. So now what we are going to do is we are going to combine R and L and R and C and also RLC together, and we are going to find out how far it is having some phase difference with respect to EMF, basically the current. Okay, right? Fine. So to begin with, we are going to discuss on AC in RL circuit. So obviously we will take a resistor combined with an inductor in series connected with an alternating current source. So this is going to be E naught sin omega t, correct? And this is going to be the resistor, this is going to be the inductor, and there is going to be a current flow of I, right? So whenever I am connecting a source of potential along a series combination, there will be same current, yes, but individual components will have potential drops, correct? Okay, so I consider the potential drop across R as V naught R, and I am only considering the magnitude. Okay, so and this is going to be V naught L, right? So this is going to be the potential drop across resistor and the inductor when I am passing alternating current in. Okay, and we know pretty well according to Ohm's law, right? So V naught of R can be written like I naught into R. Likewise, V naught L is going to be equivalent to, so I naught XL, right? So where XL is nothing but the reactance of inductance, which is nothing but the resistance offered by the inductor. Okay, so this is what is going to be the potential drop across this. Okay, we were discussing on phasor diagrams, correct? If you have a resistor, what will be the phase with respect to potential and current? They both are going to be in phase. So if this is going to be V, it is going to be I, correct? At the same time, for inductor, if the current is going to be I, right? So what will be the potential? Potential will increase or lead with 90 degrees. So this is going to be VL, correct? Yes. So if this is going to be the current and the voltage will be leading by 90 degrees. Okay, right. So first we will convert this entire circuit into a phasor diagram so that it will be easy for us to evaluate what is going to be the current. See, first what we will do is we will have, first we will go for potential drop across resistor. Okay, so what we'll get, if this is going to be V naught R, so the current will be in phase, correct? Yes. For the case of inductor, the current will lag by 90 degrees, correct? Which means the voltage across the inductor will lead by 90 degrees. So if this is going to be I, so this is going to be VL, which means exactly it is going to be V naught L, right? So the resultant is nothing but, see, this EMF is only getting splitted into two potential drops. Yes. So if this is V naught L and if this is going to be V naught R, the resultant should be somewhere here, correct? This is going to be your E naught and this is going to be omega t, and the phase angle between EMF and the current will normally be phi, correct? And if this is going to be omega t and if this is going to be phi, then what will be this? Omega t minus phi. Yes. Okay, so now you have a triangular here, right angle triangle, correct? So you can go for Pythagoras theorem. Ultimately what we require, we are going to supply it with EMF and we are going to find out the current. Actually, you are going to supply with EMF and you are going to calculate the current actually. Okay, so now according to this equation, so E is equal to VR plus VL. Since it is a rotating vector, we can calculate it as vectors also. So this is going to be the condition. Okay, so if this is going to be this, okay, right? So now according to Pythagoras theorem, So E naught square in this case, okay, E naught square can be like V naught R the whole square plus V naught L the whole square. Correct? Hypotenuse square is equal to adjacent square plus opposite square. Adjacent square is V naught R and this is going to be opposite, right? They both are going to be parallel. So can I take this as V naught L the whole square? Yes? Okay. So you know what is V naught R? It's going to be I naught R the whole square plus V naught L is going to be I naught XL the whole square. Correct? What I want? Current. So I take this I naught square common out. So what will get? R square plus XL square is equal to E naught square. So I naught square will be E naught square divided by R square plus XL square. So you can rewrite this as I naught is equal to E naught divided by root of R square plus XL square. Yes. So this is going to be the current, which is nothing but the magnitude of current which we get. And see this term, root of R square plus XL square. So this together we normally see, basically we know I is equal to E by R. Correct? So anything which is going to be divided with respect to EMF, which is going to equate with current, then the dividend is going to be resistance. Yes or no? Correct? Yes. So before that we were discussing individual components, right? So adula kuda inductor paakumbodhu XL nu vanduchu, we were discussing that as resistance offered by the inductor. So this is nothing but the resistance offered by the combination of resistor and the inductor. So we normally call this as impedance. Okay, and it is normally mentioned as Z. Is that clear? Right? So now you can now you can rearrange that equation as I naught is equal to E naught by Z, where Z is equal to root of R square plus XL square. And you know very well, since XL is equal to omega L, this Z will turn out to be root of R square plus omega square L square. Okay. So coming back to this, so this diagram, this is nothing but the phasor diagram. You can see this is going to be the triangle where the angle is phi, right? So if this is going to be the angle, we can find out the phase angle also by using tangential equation. Okay, so because since it is a right angle triangle, so you can rewrite that or redraw that particular part alone as phi E naught, and this is going to be VR, correct? And this is going to be the origin. Okay, and this is going to be VL. Yes, correct or not? Right? So if this is the case, then tan phi will be, what is tan phi? Opposite by adjacent. So opposite is VL, adjacent is going to be VR. What is VL actually? I naught XL divided by I naught R. So cancelling I naught, you will get XL by R. So tan phi can be written like XL by R or omega L by R. Right? So this is how you can find out phase angle. Is that clear? So this is for combination of resistor with inductor. Okay, and you have something called as power factor. Okay, we call them as power factor. We can also find out cos phi. So cos phi is nothing but what? Adjacent by hypotenuse. Here the adjacent is nothing but R and hypotenuse is going to be what? Together Z. Right? You can use this also to find out, but basically we use this with RLC. Okay, we'll see what it is. Right? Fine. So இப்போ நம்ம என்ன பண்ணிருக்கோம் அப்படினா EMF வந்து E naught sin omega t, கரெக்ட்டா? கரெக்ட்? நமக்கு வந்த கரண்ட் என்னவா இருந்துச்சு? I naught sin omega t minus phi. எப்படி இத நம்ம கண்டுபிடிச்சோம்? See this. This is nothing but the current. The angle between the x-axis and the current is what? Omega t minus phi. So omega t minus phi means phi angle is getting reduced, which means it's nothing but lagging, right? See, normally when you have a pure resistive circuit, the EMF and the current will be in phase. If you have inductor circuit purely, right, the EMF will lead the current by 90 degrees or current will lag the EMF by 90 degrees. If you have combination of resistor and the inductor, the phase angle cannot be 90 degrees pakka. Okay, because there will be some resistance which will have some potential drop across that too. So there might be some lag with respect to the current. So we are not sure that it is going to be 90 degrees when you combine the resistor with an inductor. So we get what? I is equal to I naught sin omega t minus phi. Last case we were discussing phi as 90 degrees. But in this case you cannot have like that. Okay, right? So this is what is the derivation for the combination of RL in AC. Clear? Do you have any doubts with this? No? Shall we move on to the next one?